Okay, so for P4.3, potential difference, and what we need to know about potential difference is that if I've got a circuit and I've got a light bulb in my circuit, and I'm sending an electron around the circuit. Okay. Now, the electrons go around the circuit and the light comes on. That's what we know so far. But why is that? Why does that happen? If you remember that the electrons get given energy by the bulb, by the cell, sorry. So they get given energy by the cell. And then, so they go around the circuit and they're carrying this energy and they're going around, and then they get to the component. And the component's really hard to get over. So once it's gone through the bulb, it doesn't have as much energy anymore. And then it goes back to the cell. Okay? Where does that energy go? Well, that energy gets given out as light and heat from the bulb. Okay? And let's say we've got a 6-volt cell here. That means that's the amount of push these electrons are getting. Well, then my bulb will be using 6 volts. So if I put a voltmeter here, and I'll talk to you more about voltmeters in a minute. If I put a voltmeter here, that voltmeter is going to be measuring 6 volts. But why is that? Okay, so first thing we need to know is what's a voltmeter? And the second thing we need to know is, why did I stick it in like this? Okay, why not just put it in the circuit? Why do I have to create an extra circuit to put the voltmeter on? So it's very confusing. But if you think about it, let's simplify it. Gave it loads of energy, it went into the bulb. By the time it gets back here, these electrons can't have energy left. Okay? So loads of energy given here, no energy left here. And that's because there's only one component in here. So that means that this component must use all the energy. And that's the same as saying that this component must use up all of the volts that the cell provided. So let's do a little bit more about what a volt is. So a volt, or potential difference, more accurately, and it's measured in volts. So potential difference is what we're talking about, and it's measured in volts. And that equals the amount of energy that is given to each unit of charge. Okay? And the units for energy are joules, and the units for charge are coulombs. And if we wanted to write that out in an equation, we would write V equals E over Q. Okay, where E is the energy, Q is the charge, V is the potential difference. So energy per unit charge. And if you look, these electrons, they're the charges. So it's how much energy are you giving to each one of these charges, and then how much energy they've got left on the way back. Now, the next question was, why did I put the voltmeter like this? Well, what I'm doing with my voltmeter is I'm measuring how much energy does it have here, and how much energy does it have here. So I look at my electrons and okay, how much energy do you have here? How much energy do you have here? And whatever the difference in the energy is, that is how many volts have been used up, and that's why we call it potential difference, because I'm looking at the difference in energy between here and here. And I know that here, my electrons have got 6 volts of energy per unit charge, and I know that on this side, they don't have any. They've got 0 volts per unit charge, okay? Because I know that by the time they've got to get back there, they've got to have 0, but there's nothing else using up any energy after that light bulb. So the difference between 0 and 6 is 6 volts. Let's go for another example. This time I'm going to use 2 resistors. So this is my 2 resistors, and again 6 volts, and again my electrons go around the circuit, and then they get to this resistor. Now it's not easy to get across that resistor, so they lose some energy. And then they come to another resistor, and they lose some more energy. When they get back here, they don't have any energy left. So we know we start off with 6, we know we end up with 0 at the end. So if both of these two have got the same resistance, if they're both 100 ohm resistors, then they're both going to need the same amount of energy to get across them. So if I put a voltmeter here, and I put a voltmeter here, and I put a voltmeter here across both of them, why not? Okay, and I call that one V1, that one V2, and this one V3. Okay, well, first of all, let's do V3 first. How much energy do these electrons have per unit charge? Well, we know that they've got 6. And how many do they have per unit charge here? Well, we know they've got 0. So that means the V3, which is across both resistors, is 6 volts. And we knew that because that's just the total voltage in the circuit, and what that's doing is it's measuring across everything that's in that circuit, so it must be 6 volts. Now it gets a little bit trickier. Let's have a look at V2 and V1. Well, because they're the same, we know that it's going to split evenly. Okay, they both need to use the same amount of volts per unit charge. So I need to divide 6 by 2. So I've now got 3 volts there and 3 volts there. And what's happening here is you start off with 6 volts here. So if I measure how much energy this electron has, I would say that electron has 6 volts. And if I measure how much energy per unit charge this electron has, I'd say that one's got 3 volts per unit energy per unit charge, and then here is down to 0. So 6 minus 3 is 3, 3 minus 0 is 3. So it must, because it's even, they've got to add up to 6, and they've got to be the same as each other. Okay, so the next thing I'm going to talk about is an experiment that we can do to calculate resistance. And it looks like this. What you want to investigate is you want to investigate how does current change with voltage. So we're looking at a graph that looks like this. Current here, voltage on the bottom. Okay. So I want to know, what I'm really interested in is how does current change with voltage. Okay, so I'm going to do an investigation. So I need to measure the current and I need to measure the voltage. Well, I've told you the equipment that measures voltage, that was a voltmeter. And the equipment that we need to measure current is called an ammeter, and I'll draw the circuit now. So the circuit is here. That's my ammeter. That's my resistor, that's my component that I'm investigating. And a key thing to note is for the ammeter, it's in series, which means that it goes ammeter and then resistor. So this is a series circuit. It just goes round and round and round, and the electrons don't have any choices whatsoever. So it goes episode 1, episode 2, home. That's a series, like a TV series, where one episode follows the next. And then I need to put my voltmeter. And the voltmeter is in parallel, because remember, I'm interested in the difference in energy per unit charge that is there compared to there. Okay, and then I measure, and then I change my voltage and measure my current. So 1, 2, 3, 4, 5, 6, 7, and so on. Okay, and let's say it goes 5, 10, 15, 20, for example. So for 1 volt I got 5 amps, for 2 volts I got 10 amps. Remember to always put your units on the top. So if I put that here on my graph, I'm going to go from 0 to 10 there, and I'm going from 0 to 20 here. And I want to then start plotting in my points. So so you can see that on my graph here, for a resistor, when the current's 0, the voltage is 0. Well, we'd expect that. And we can see that it's got a nice straight line. So as I increase my voltage, my current is increasing, and it's increasing directly in proportion to my voltage. So the first thing that we can say there is we can say that V is proportional to I. As voltage increases, current increases. That's the first thing. And in physics, what we can do is we can say, if you have this proportional sign, we can say that V equals some constant, which we call K, times by I. Okay? And now we can see that we've got a bit of a we've got a situation where we've got a graph and we've got an equation. So you know that y equals mx plus c. Okay, where this one is the y, so current is the y, voltage is the x, and the gradient is m. And I need to work out what my gradient is by doing a triangle like this. And when I do my triangle, what I need to do is I need to work out, so that there, so that's about 2 or 3, let's call it 3, and that's about 20. So this here, so my y, and we use the delta, remember from the previous module called change. So change in y is from 3 to 20, and delta x is from 1 to 10. So I can say that delta y equals 20 minus 3, and I can say that delta x equals 10 minus 1. So this one is 17 and this one is 9. Okay, so that's delta y and delta x. Remember, that just means change in y and change in x. And from my graph, you can see the change in y is from there to there, so from 3 to 20, and change in x is from 1 to 10. Okay, so then if I want my gradient, if I'm using y equals mx plus c to work out my gradient, well, I know that I went through the origin, so I can make it really straight. I can simplify it, so I can say that c equals 0 because it went through the origin. Remember that c is the y-intercept. It's where it crosses this line here. So if it had crossed it up here, it would have been 10, crossed it here, it's 15, and so on. So it's where this blue line crosses this y line. Now, so I've simplified that now to y equals mx. So if I do m equals y divided by x, and I know what my y divided by x is because I've just worked out what y and x is. So that means it's 17 divided by 9, which is nearly 2. Okay? And my y is my current, and my x is my voltage. And what I can then do with that is a very clever chap called Ohm. He discovered something called Ohm's law, and he noticed that if you got a nice straight line like this, it meant that the gradient's not changing, which means that your constant isn't changing. Okay? And if your gradient's not changing, then what it's telling you is that the resistance of the component isn't changing. And he wrote a law that went like this. It went volts, or voltage, or potential difference, equals current times resistance. And if that line was a straight line, then what you got was you have a constant resistance. And only special components have a constant resistance. So then if you want to work out what resistance is, you need to do, that's V, that's I, that's R. You then need to do R equals V divided by I. And on our graph, remember that our graph, that means that is equal to the x-axis divided by the y-axis on our graph, because we worked out, and when we worked out the gradient, we did y divided by x. So if we want to work out what the resistance is, we need to do 1 divided by our gradient, because what we want to do is we want to have the y on the top of this divide and the x on the bottom of this divide. So we want to flip it around. So we do 1 divided by the gradient. So 1 divided by 2. So in our example, the resistance of this component here, because we worked out the gradient to be 2, and we know that resistance is 1 over the gradient from Ohm's law, voltage equals current times resistance, then the resistance of that component must have been 0.5. And you can check this, because if you wanted to, you could measure the voltage and the current and see if it always was. So if you times the voltage, if you divided the whole voltage by half, do you always get the current? So you could check that using your equipment. That is quite tough. You might want to review that a couple of times, and I'm sure you'll do the experiment in class.